Yeah, thanks, Timo, for the nice introduction, and thanks, Scholz, for the invitation. Today I'm going to talk about closed-loop transcranial electric stimulation, what all the bits and pieces are, and how to, well, do it. Okay, a short overview. So first I will start about talking about transcranial electric stimulation. What is it? What is the efficacy of it? How it depends on several confounders and several things in the study design. Some words on entrainment and very important about safety. And then I will introduce you the closed loop design, what to do before, what we did together with the Charité, Professor Brandt and Professor Obermeier had a joint grant, and Dr. Schmidt and me were doing the studies actually. And then I will close with why real-time equipment is so important in doing this right. Okay, transcranial electric stimulation. Typically it's done with 2 electrodes, sponge electrodes, but it could be more electrodes. But we always have to keep in mind that where the electrodes are, there's also the EEG cap, and of course, the recording would not work in the vicinity of those electrodes. So typically 2 electrodes are used. The application is it's very small current. So the current outflow is like 1 milliampere, 2 milliampere, but that doesn't mean it's harmless. It's a non-invasive method, and the idea behind is that the electric field done by the current alters permanently the firing probabilities of targeted neural assemblies, and thus might help to increase function. It is not painful. There's a small tickle, but definitely no pain. And before we come to all the problems with it, I'd like to tell you why is it used. Well, often no realistic therapeutic option exists. Like in our case, we deal with stroke restitution. So patients having a stroke and are slightly recovering from it, but could need some help. Especially the motor cortex could need some help. But there is no therapeutic option for this. Of course, when it became a hot topic in the last decade, it is also used, of course, to gain a better understanding of brain functionality. What does what, and what are the bits and pieces? What are the roles of oscillatory rhythms? What is the effect of the phase reset within that rhythm? Why is it happening to a specific time, and so forth? The mode of action of TCS is still somewhat unclear. Parts are known, parts are obvious, other parts are not that easy. We'll come to that. So what forms do exist? Historically, it started with a DC application, so direct current, just plus minus. And there, the mode of action is very simple. Just by shifting the membrane potential, either in a hyperpolarized or in a hyperpolarized state, the neurons are more likely or less likely to fire, and that increases or decreases the firing rate. That's pretty simple, but normally people nowadays either use noise, random noise, TRNS, or alternating current. That is because with alternating current, we have more parameters, we have a frequency, and we can try to target specific brain rhythms. A very important question and a very, well, sort of funny question is who can, or better to say, who is allowed to do it. Interestingly, there is it is never approved in animal experiments. The thresholds which we should use or which we should not violate are pretty soft. And I come to that point, they are often also misunderstood, and all of them are defined post-hoc. So people were doing experiments, and after literally nobody died and didn't feel any harm, it was considered safe. In fact, there is no certificate, profession, or other whatever required in healthy controls, of course, to do that. On patients, this is different. But actually, anybody can do it. Now, this is different from everybody should be, of course. So the question is, of course, is it safe? Well, considering that the goal is to induce plastic changes to the brain, definitely some caution would be appropriate. And I would suggest that there is a profound knowledge of anatomy and function of the involved brain regions present. And this is often overlooked, and this is why I'm doing this talk today, the same holds for the physics and the electrical properties. So, in other words, the perfect team would be a medical neurologist and an electrical engineer. And of course, we should do everything we do with a minimal energy principle. I come to that later again. So how safe is safe? Well, in general, one always tries to apply as little energy as possible to a patient or to a human subject. This is totally independent of the method and the purpose. We always try to do as little intervention as possible. Now, the electric energy is defined as electric power over time, but it's of course not that simple. The electrodes we're dealing with are sponge electrodes. They are not pointwise. And actually, the entity we should observe is not the current, but the current density. So that's the current flow per area. And it's, of course, not at the site of the electrode important. It is important to restrict the current density inside the brain and not on the skull surface. The problem here is that we cannot measure that, and that the human head is very complex in electrical properties due to volume conductance. So we should actually do some finite element modeling or boundary element modeling of a head. These are available just to have an estimate of what we are doing here. Is that 1 volt per meter electrical field, or are we talking about 5 volt per meter electrical field, or are we talking about 50 volt per meter? And of course, it is even less reasonable to just observe the current flow out of the electrode, or better to say, even in the electrode. Well, typically, people write in papers things like, we used 1 milliampere. Yeah, 1 milliampere of the current source into the electrode, but that's totally ridiculous. What we are interested in is the electrical field inside the brain. That has to be limited, and not the current into the electrode. And this also leads to problems when people change electrode. So we are doing the same thing as the other guy. Yeah, but you're using a very, very small electrode, so the current density is much higher. And some people have problems with these concepts. This is why I'm saying it is very, very, very important that there should be somebody in the group, in the study group, who has access to that knowledge. The current density is quite obvious, quite different for different sized electrodes and also for different shapes, because it's the current per area measure. Yeah, and it's also affected by the electrogel we use and everything. Another important thing is when we're not using a totally balanced stimulation scheme, where the integral is 0, which also holds for parts of the signal, additional problems should be considered, or considered. Yeah? Any substance used in the vicinity of the electrodes must not contain any ions, or at least be tested independently as safe, because any DC part in the stimulus could transport the substance through the skin. And some substances split up in electric fields, changing their properties and causing a lot of problems. So regarding the electrode position, this is a very important part. Really great care should be taken. I've read studies where people moved the electrodes from here, let's say, to here, got a better signal, were happy, published that. Well, the problem is that there's also other brain structures, like the brainstem. And the brainstem should not be tampered with by any means. It should not be touched. It should not be affected. Yeah? And this is the other reason why I really suggest to do a modeling first. I mean, there's models online which you can use. Walter's book, for instance, Professor Walters offers this, such that you can see, okay, if I do this, this would be happening. And I look into the brain and I see, okay, the brainstem is unaffected and also the hippocampus is unaffected. Or something, yeah? And I really suggest to always discuss your experiment with a medical expert, from my point of view. For a medical expert, I would suggest always discuss this with an engineer. And I really do this. After having like 10 years of experience, I still do this every single time. When I do an experiment, I call my friend and we discuss this. Just to make sure I'm not goofing up here. And we should also always start very conservative. When I calculate something and think, okay, this should be the effective dosage, and this should be correct with respect to the current density, we start with 1% of that. We carefully monitor the subject's condition, preferably by a medical doctor, and this is also just a psychological effect, but it's also a really safety issue. There should always be an emergency switch nearby, both to the experimenter and the subject. So in fact, in my lab, I have two. One is at the desk where the human subject sits, and one is in the next room where I actually watch the participant through a window. And this shortcuts everything. And of course, a more general advice, know your stuff. So, well, this is always a good idea, but especially here, we are dealing with humans and we are changing, or the goal is to change something in the brain. Yeah, this is, you must be sure what you are doing. Okay. The traditional design, which is like 20 years old or even older, it goes like this. So we do a 5 to 10 minute baseline measurement, and what we measure is more or less general things. I come to that this is not optimal in a few slides, but this is a traditional design. So we do like the baseline, then we do 10 to 20 minutes static stimulation, and then we make a post-stimulation measurement. That's a general approach in clinic. However, when we do it like this, we see also in the literature, we see a huge variety of opposing effects people observed. And this is just an overview of what affects this. It's like, is the electro position different? Are we actually measuring the same thing? Might the task be different of the human subject? Are the simulation parameters similar? Is the subject coming from a comparable study group? And other random effects. And I look into these in the following slides in more detail. When we started our closed loop run, so to say, we found out that we actually could not build on things published already, because for every paper which states one effect, you find like 2 papers stating the opposite. Now, considering that we are not the only clever guys, there must be something generally left out. So we compiled some information from the papers and from other groups, what they were doing for stimulation, what they did measure, and what the effect was. Most people do CSE, which is cortical spinal excitability. So it's basically a motor threshold defined by TMS, and then you do some simulation, and then you see the motor threshold is lowered or increased. So it is more or less likely for the brain to respond. So the whole brain is more active. That is the effect when the CSE is higher. Well, it is probably not very specific, this measure. Why is it then used? Because it's simple. Yeah? So we set up a study. We did 30 subjects, of course, double-blind, and we tried to do our own base data. Yeah? So we did like 7 different stimulations, every week a different one, on the same people. Half of the study group was doing finger tapping, FT. So the goal is a very simple motor task. You just have to click as fast as you can for 30 seconds with your fingers. And we measured the force applied, we measured the rate and everything. And the others do a simple go-no-go task. So you have a fixation cross, and then next comes either a red or a green ball. And when it's green, you click a button. And 9 out of 10 trials were green and 1 was red, on average. And then after the stimulation session, everybody was tested on both of the tasks. What was the effect of the stimulation? And this is just some examples to illustrate that the stimulation effect depends on a lot of things. And when the people did, for instance, a different task or something else, then it's no wonder that one group reports one effect and another group reports a different effect, because it's a joint thing. It depends on the stimulation and the task and a lot of other things. So in this example, we stimulated with random noise, and we see that for the go-no-go task, so this means that the people were doing the go-no-go task during the simulation. Yeah? These 15 people had a lower CSE, whereas the people doing finger tapping had a higher CSE. When we stimulated with gamma, the picture was just the opposite. Yeah. So for the go-no-go task, it decreased, and for the finger tapping, it increased. But that's a different frequency. Gamma is responsible in motor for fast movement, whereas beta is related to holding. Yeah? So when you pre-innervate, you grab something with force. Now my beta is high. When I'm intending to move it, I have a short pulse of gamma. Okay. So the TSES simulation effects strongly depend on the subject's task during the simulation, and that was often overlooked. As I said, the classical design is to do nothing. Well, doing nothing is not that simple. People think something, and we found out it's much more controlled if we force the people to do something such that they're concentrated on doing something. Other things we observed is, for the go-no-go task, you have, of course, a reaction time. How long after the green green bullet does it take to hit the button? Yeah? And the precision measure is basically the false rate, error rate. When we measure reaction time for a stimulation with beta frequencies, we get an increase where we get a decrease when we stimulate with gamma. You can look at the sham. Why is that changing? That's because of motor fatigue. When we look at precision, it's exactly the opposite. Yeah? So it depends on the task that people do. It depends on the stimulation frequency we use. And of course, it depends on what we measure. And when we look deeper into the data, we also find out that it also depends on the performance level of the subject. So-called high performers need a different stimulation than people which just learn the task. This is the bonobo slide that was even more obvious for the finger tapping. Okay. How is efficacy measured? I subtitled this "A Word on Entrainment," this slide. Most publications refer to entrainment when reporting effective stimulation paradigms. So they say something like, yeah, we have frequency entrainment, or we have phase entrainment. And based on that, the reasoning is, and this means the simulation was effective. However, entrainment is not very well defined, actually. Now, we differentiate, therefore, between frequency entrainment. Frequency entrainment means that the endogenous brain rhythm we are targeting, there's a frequency, let's say beta or gamma or whatever, that this frequency shifts in its frequency towards the driving frequency, the stimulus. To do this, we need a very hard drive. I mean, let's consider we are not talking about the brain, but we are talking about an oscillator. An oscillator has an eigenfrequency. If we force that oscillator to vibrate with a different frequency, we need a real hard drive. It is doable, but you really need a lot of energy. This means that frequency entrainment is rarely observed. It is almost exclusively observed in studies where the safety limits were either ignored or misunderstood. Like I've seen the poster where they did not use sponge electrodes, but these were epilepsy patients with very, very small ECOGs implanted. And the electrode size was like 2 millimeters, but he still used the milliampere. That's, of course, 1,000-fold the current density. And he observed frequency entrainment. Mostly it's observed in animal studies. Phase entrainment is a little slighter form of that. It means that the phase of the endogenous frequency shifts towards the driving phase. We need a less hard driving here, and it's observed, but the driving frequency, of course, needs to match the rhythm, the endogenous rhythm. By the way, both of this and all of it actually is in very well. It's very well described by simple linear system theory, how to drive an oscillator. And a term we use, or we try to implement, I would say, is we call it periodic enforcement. And that means that the endogenous rhythm is amplified. Not saying how we do this, but we just measure the endogenous rhythm. And if it gets more by power, no shift, no frequency shift, no phase shift, this is probably more what we wanted. Yeah? Because what is often overlooked is this, with the exception of a maladapted rhythm like a tremor or epilepsy outbreak or something, it is in general very questionable if the frequency of phase entrainment would actually be beneficial. I mean, we're tampering with a system we do not completely understand, and we make it vibrate with 30 hertz. So what? Is this good? We don't know. So we tried to do it a little different. The original idea was to more focus on individual brains and individual situations of patients. So in the last 10 years, let's say 5 years, the term closed loop is somewhat the buzzword of the decade for electrical stimulation. However, the principle is of course not new. It is every student gets this taught in control theory. The idea is, instead of steering a system, it is much better to add a feedback loop where we control, is what we aimed at, actually did it happen? And if not, we could adapt our stimulus to make it more like we wanted to do. So it's much more robust control, of course, and it's at least in principle, it's able to deal with adaptation phenomena within the brain and also with individuality of patients and subjects. However, we have some prerequisites for doing this. We need, on this side, a very fast observable, either functional or behavioral state variable. Things like cortical spinal excitability is neither functional nor behavioral. It is when we want to increase the frequency of finger tapping, then we should measure exactly this. If we want to increase the force somebody uses in gripping something, then we should measure the force. This is what I'm saying. We need, of course, a complete control over the stimulus parameters, and that is a problem because earlier it was only thought that the frequency and the amplitude of an alternating current is important, because when we do it hard enough, we have a phase entrainment anyway, but we found out that this is not true. We also need to control the phase of the stimulus, the phase between the stimulus and the endogenous rhythm we are targeting. If we, let's say, measure a sine wave within the brain, we should not, or at least do it intentional, stimulate with a cosine. And due to this, we need a strictly real-time capable system. However, we also need to do something first. One, if not the one prerequisite for setting up such an adaptive closed loop simulation is, of course, that we have a short stimulation which has a repeatable effect. So we only have a short time of applying the stimulus, then we measure, and then we repeat. We need to measure in between. So also the stimulus application is also short. Remember, I said in traditional design, it's like 10 minutes. You can't do a closed loop with that. We have seconds. And the other thing is that the short measurement also must contain enough information to adapt the stimulus. If you just measure noise, this is not enough. So, and although our field of interest is stroke restitution and that's motor control, which involves beta and gamma frequency, it makes, of course, much more sense to start with something simpler, much simpler. Beta is a very complex rhythm. So we focus on alpha. It's a way stronger signal, it's a much simpler form. And the argument is, if we can't do it on alpha, we shouldn't try on anything more complicated. So I came up with the following idea. We have, in yellow, we see the stimulation. It ramps up, it stays up, it goes down, and this is seconds. So we have like 5 seconds of stimulation. And we use the Berger effect. So when you close your eyes, the brain typically responds with a very fast alpha rhythm. I mean, not fast in frequency, but with a fast onset. So after the eyes open stage where we apply the stimulus, it's either that the subject has the eyes open for another 3 seconds and then closes it, and then we measure both periods. And we also changed it that the eyes were closed first, and we also measure this to check for after effects and stuff. This was a general setup, and we repeated this a couple of times, of course. This was just to implement first our stimulus does something, and we could measure the something. Okay. What did we observe here? Well, ignore the black one. If we just focus on the red one, which is a difference to a sham stimulation, we see an increase of our alpha frequency. So yes, our short-term stimulation does have an effect. We stimulated the subjects with their individual alpha frequency. So everybody has an alpha frequency between 8 and 13. In this case, it's like 10.5 or something, 10.6. And we measured that first, and then we stimulated every subject with its individual alpha. However, when we stimulate with different frequencies, so we stimulated with a complete volley of different frequencies, we don't see an effect. That's always the same person, and we stimulated with 9.5 hertz, slightly off. We stimulated on spot, we stimulated with 15 hertz instead of 10.5, and we stimulated with 60. And we basically see the same picture. But it has an effect. Okay. And if we focus on single trials, so one measurement, then we see that the power has a huge variance. It's 2 orders of magnitude, actually. Well, in some cases, there was no onset of alpha, yes, but still, this is very huge. And the obvious question is, where does that variance come from? So the hypothesis here is that the phase difference between the stimulus and the endogenous rhythm is crucial. So I checked for this, although I didn't have by that time any equipment of controlling the stimulus with respect to the endogenous rhythm. You can post-sort your data, of course. So the problem is that the phase of the stimulus is random, because we don't know where the zero crossing of the endogenous rhythm is. But even upon random phase stimulation, we should be able to sort the trials, and the effect strengths should be associated with that phase difference. Did we hit it by chance, or did we miss it by chance? And that should be measurable and should be associated with the strengths of the effect we see. So if I plot just the phase before the simulation, just the phase distribution and start of all the subjects, I don't see a clear picture. When I look upon the responses, the strongest individual response for every subject, I found for all subjects that this happened, the strongest response always happened at the smallest phase difference. So in some cases, out of 100 trials, we just hit it a couple of times. And all of the red arrows, all of these were the strongest response for every subject. So first, we don't have any phase entrainment thing, because then all of them would be here, or most of them would be here. But the effect strength is phase dependent, so we should control the phase. And luckily, I was not the only one doing this. Professor Ziemann did this with TMS and also published this very high. So that gave me the additional argument why we are doing this, what we do. So why is real-time the answer? Well, first, I'd like to say it once again, the high variance up to opposing effects is all over all transcranial electric simulation publications. We do not have a precise control of a stimulus onset with traditional equipment. In fact, most EEG systems don't even have a live output. There are some, and they're getting more, but some used still don't. And if they do, they unfortunately use inappropriate protocols. When I was buying my equipment like 3 years ago, there was one company using USB, which has like 6 milliseconds jitter. Almost all other use TCP/IP. And just to convince you that this is not just made up, TCP/IP has a jitter of up to 500 milliseconds. This is the measure of my computer, and it was a direct cable. It is not a Wi-Fi connection. It is not something which is going through routers or anything. It was a direct cable connection. And what you see is that there is a considerable jitter all the time, and there's also peaks which are really bad. That like half a second the system waits for a packet. That is a good computer, by the way. So it can get worse. TCP/IP, why is this? TCP/IP is not made for screening. TCP/IP is made for making sure that many packets go a long distance and could be assembled in exactly the order they were sent. But it is not a real-time protocol, not even close. Now, milliseconds is fast. Why do we need to do better? And that's just a small calculation here. So when we want our stimulus onset to be controlled, to have less than 5 degrees phase ambiguity with the endogenous, let's say, beta signal. Like we're trying to hit the zero crossing of the beta signal in the brain, and we say, well, 5 degrees off plus minus is good enough. Then we can do the following calculation. The beta signal has like 30 hertz. So we would need a precision of less than half a millisecond to do this. We have like 33 milliseconds per full cycle for the beta signal. We said we accept 5 degrees off, that would be 0.6 milliseconds. When we want to investigate these phase effects and how to increase or decrease a rhythm, the idea is, of course, that when we hit the rhythm, we would increase it, and when we be just 180 degrees off, then we could dampen it. To do this, we would need an EEG sampling rate of above 2 kilohertz. We would need an output protocol of the EEG system to have at least less than half a millisecond jitter. All of these are cumulative, of course. And we, of course, need a data analyst. And here, I mean, the live data analyst. We measure the signal. And of course, we have to analyze it in a way because we want to know, should we change the stimulus on the fly? So also this data analysis must have stable calculation times. Fortunately, such components do exist, at least almost. So first, a word on computational jitter. When we program things we are always thinking, hey, our computer is so fast. I mean, it runs in a gigahertz regime, and so it is always as fast. That's not true. For a normal, that's a normal laptop, but it's a dedicated CPU. So I made sure that nothing else happens on this core of the laptop. And then I do very simple program. It's an empty loop actually with a 1 millisecond wait. So it does nothing. So no parameters change, no calculation changes, no shared resources, nothing which complicates the picture. Just a millisecond wait. And then I measure what happens. Because you can't read it, because I made this very small, here is the 1 millisecond. Yeah. Actually, we would have expected a line here. Yeah. But what we see is that every other loop takes 2 milliseconds, and once in a while there is something which takes like 16, 17, 18 milliseconds instead of 1. That's the same picture on every ordinary computer. It doesn't matter if it's Windows, Linux, Mac, or the brand, nothing. This is just because on a general computer, we have like an opportunity operating system. In easier words, that would mean you click something and want something to be executed. And the operating system tells you, I understand what you say, I do it when I feel like. It does a lot of other things in between. Yeah? I do this on a real-time Linux kernel, which is a very restricted operating system. It's not strictly real-time, but it's much better. Huh? In fact, this is the component I use for a real-time system. This is from National Instruments. It's a computer which runs under real-time Linux. And what you see is that this is again the 1 millisecond. You see much less taking 2 milliseconds and only a few taking longer and not as bad as here. But this is still not even close to determinism. Now, these real-time systems have another thing. They have not just only a general CPU, they also have a few programmable gateways inside. It's an FPGA, which actually implements the code in hardware. It's like an EEPROM, which does this function you program then on the chip. Now we have determinism. Yeah, this is 1 millisecond wait, and this is exactly 1,000 microseconds. Okay. Now a millisecond is actually not good enough for what we are doing. If I go down to 25 nanoseconds, I still have the same picture if I program this right. So in other words, I can make sure that, in fact, the compiler of this system makes sure when I give the loop a time constraint and say, hey, you must be finished within 200 nanoseconds, the compiler tells me, of course, or no, actually, I can't do this. But you know before you run the code that it's either possible or not. 200 nanoseconds is a long time for such a machine. So the important part is the real-time kernel of this, and of course the dotted bright yellow lines. There's a lot of things you don't need to do in real time. It's just enough if you, let's say, start the experiment and you know when actually it started precisely. But for a lot of things, for some things, you do need actually a real time. Because this is an EG group, I'm using the new one, a Tesla system, because basically, because, well, it's a very good system, but the very important feature is that it not only uses a slightly better protocol, it uses UDP broadcast, but it has 16 direct analog odd channels. So the signal picked up from the electrodes is gone through only the fixed runtime of AD converters. So it is once AD converted to a digital signal, and it goes over light fiber, and then it's converted back, and then I have an analog system. This has a fixed runtime. Every single bit going over this line takes exactly 2.3 milliseconds to arrive. Now I have 16 out of my 64 channels directly analog, and the rest I have, as we all know, in blocks of data. Now with 1/4 of the signal, because the signals should be the same, I should be able to establish a phase locked loop within my system. So I know these analog signals come and were sent 2.3 milliseconds before they arrive in the system, in the serial. And the block data, the other part, the other channels come whenever. But I know it's the same data, so I could shift it, and then I know for every single block of data when exactly it was recorded, not when it arrived. And of course, the idea behind the whole thing is to hit with my stimulation exactly the zero crossing. Well, I could not hit the zero crossing. I could hit the next zero crossing. I know the frequency of my signal. I know, well, this packet was sent then, and I know when would be the next zero crossing. I know all the times how much time do I need to switch this on, how much does this system need, the simulator, to do something, and then I could hit it, the next zero crossing of my rhythm. I'm not sure it would work for gamma, but actually I know only one lab in Germany who's able to record consistently gamma in Freiburg. So for most of the things I'd like to do, this would be enough. And of course, I could always, well, the idea is to align all data, all events, all everything on a unique time axis, and then do all my data processing afterwards with respect to that unique and verified time axis. And during the experiment, every time this is checked and checked and checked and checked. Okay, yeah, that's the design. Some considerations, what should go where? Well, the obvious question is why not process everything on the FPGA system? I mean, it's the only one which actually is good enough. Well, the FPGA is pretty limited in size. You have not much RAM there, you have not much slicers, you have not much space. So possible calculations are also pretty limited. So you don't have floating numbers, you can't do recursions, you can't do any dynamical load libraries and stuff. So just to give you a picture, a year ago, somebody won a prize at National Instruments because he was able to implement fast Fourier transform on the FPGA. Well, fast Fourier transform, any bachelor student can do, but not in such a system. So that was actually worth the price. So what should be done where? Well, the I/O from the EEG, from the stimulator and to the stimulator, and everything which is actually measurement should be done on the FPGA. And that's also how the National Instruments designs the stuff. You can access to all the input modules only. You can access all the input modules and the output modules only via the FPGA. So phase-locked loop, fast Fourier transform, and other simple analysis should be done on the RT Linux system, because this is much more comfortable to program. And user interaction, pyramid control, sophisticated analysis, Scholz, MATLAB, whatever. This all should be done on some host, but this is typically not time critical. However, such a system is pretty complex. You need like 20 parallel, partially asynchronous loops, which always need to be synchronized in at specific points in time. You always have possible interference with already tested designs, tested loops, and tested parts of the code. Because every time you change something on the code which runs on the FPGA, you basically use the new chip. So stuff which worked because it was on the left bottom corner of the chip are now distributed, and now you have timing problems. So you always have to rerun all the tests. Yeah. You could set the wrong priorities because the RT system is deterministic because the programmer controls it, not the operating system. Well, that means also when the programmer does something bad, then something bad happens. Yeah? And so there is definitely fundamental design flaws. In other words, I am not an expert in programming this. It's my programming errors, which also still problematic. Okay, but that's basically it, and it works, it goes. And by the way, people with a bigger group and with also more money and more experience, like in Siemens group, they actually built a system which is not using a general purpose programmable real-time system, but a dedicated card, and they actually sell the system as a real-time simulating device, which is quite good. You do not have all the control I wanted, but it's a very, very, very good system, much better than anything else so far. So to sum up,
can I ask a quick question?
Sure.
I might have missed like the most important part by just shutting down my computer. So would there be in general, I mean, you're trying to reach like higher accuracy and better timing for wireless transmissions. Do you see any chance to extend that approach to a wireless setup?
It makes things, of course, a little bit more problematic because if you use a wireless connection, all the jitter problematic is like 5 to 10-fold.
Right.
Yeah. But at least partially, I would say, you need some reference signal where you know how long it travels, coming from the same device, actually, coming from the same cap. Yeah. So yeah, I have to think about this if we can also synchronize it with an artificial signal. Yeah. But what we need to know on the data analysis side is when exactly was this bit of information recorded. Of course, we know in an EEG system, okay, it's sample data, it runs with a stable frequency, so we only need one data point actually, yeah, to set the reference. But this we need, and we need,
yeah, maybe that's something we can discuss later. But that would be interesting. So we I think lab streaming layer uses like an artificial signal, it's just sending like events, but entirely different time scale we're talking about here. So,
but actually, I'm also very close to the end already. I just want to summarize what we need, and then maybe just a small picture of what the rest of our group is doing. So, I called it prerequisites, limitations, and perspectives because not all of it is still running. Actually, most of it is not running. Yet that is more or less due to the limited personnel. So we have some prerequisites for adaptive closed loop simulation program. We need a deterministic data transport and analysis. And when possible, we should use real-time equipment. And for some problems, we have to use real-time equipment, actually. We need a fast observable functional relevant state variable for whatever we're doing. Yeah? And this is, of course, a different state variable if you have a different task or a different problem. We should strictly program in modular, exchangeable, and generic software mindset. So we should be able to extend and revert to the former stage and stuff like that. So actually, National Instruments helps in this because they suggest specific designs for specific tasks. And you can program the same stuff in 10 different ways. However, on a real-time system, 8 of the 10 would not work, not really work. So, and this is quite different form of programming. We need a proper description of the dynamic properties we're observing. And this is why this is well done that I'm doing this within the group of Klaus Obermeier, because we definitely need to model the brain dynamics. We cannot observe everything. So we need a mathematical model. We test the model on some extremes, and then we can look into the model to get more understanding of what actually in the brain happens, but we cannot observe that. We need well-structured experimental designs. And although this is quite obvious, everybody would say I'm having a structured experimental design. But what we need also for the modeling to verify or falsify parts of the model and also to test parts of our strategies, we actually do need perturbation experiments. These are generally, well, they're not forbidden, but they won't be carried out in a clinical setting. The clinical setting, by definition, has to build on a hypothesis. I'm doing this to improve the status of the patient. And then I can check the effect of this stimulation and, let's say, a no stimulation, a sham stimulation. What I cannot do is the other way around. I cannot do something to make something worse. This is ethically not allowed, and there's a good reason to it. However, to some extent, we would need not only the plus, but also the minus sign. We would not be able to do this on patients. Being myself also in an ethics commission, I would not consider this okay if we do it on human controls. So we need a different strategy here to do it. And when possible, we would also need invasive ground truth. Now, this is rare and very limited, but it's possible. During the time when epileptic patients get their ECOGs implanted, you have like 5 to 10 minutes to measure something when you're calibrating the system. This is actually what people want to do. You need a precise data collection. You need timestamps all over, everywhere. Everything must have a reliable timestamp on it. You might need additional sensors for it. And I'm always trying to collect whatever data is possible. I could sort this out later when I have access to, hey, measure heartbeat, measure breathing rate, measure whatever, and do it. Yeah. Then you can check later in your data analysis, is this associated with respiratory rate? Oh no, it's not. Okay, good that I measured it. But you can't see this if you do not have a independent recording of that. We need flexible hardware designs, so we don't need a simple pre-stim post design. We would need always loops. We need to change. We observed so many things that the brain state, I was not talking about brain state because this is very contradictory, but the people are not in the brain of people is not in the same state when we do or repeat our experiment. It is always in a slightly different state. And it could be in a very different state. Like for instance, like now it's like 2 hours ago, I had a migraine attack. Yeah, my brain was in a different state, definitely. The perspectives is that we could phase lock the stimulation to our endogenous rhythm. Well, that was the starting point, so this is rather obvious, but we can do more. We can do an on-the-fly adaptation between with respect to the performance level of the subject. We can use individualized signal shapes. We could extract from our observed endogenous brain rhythm its form and use this as a stimulus. We could use spatially focusable stimuli. What I've not talked about is that people talk about targeting. Well, actually, when we do the 2 electrode setup, we hit half the brain with our stimulation. We hit the whole hemisphere, and also the rest is not totally unaffected. So we would not just hit the motor cortex or even smaller structures. But of course, when we remind ourselves what we learned in 8th grade in physics, we could do interference. So we have like 2 electrodes. We have maybe another set of electrodes where the reason is to dampen the signal outside the specific region, to cancel the signal actually, so that only a small part in a small area is effective. That needs a lot of computation, but that is possible. Walter's group does this, and also DARPA and other groups in the US with their ring electrode. And the idea, of course, coming from a machine learning group also is the idea, could we actually train a model? Could we train a model to generate a stimulus appropriate to that situation? Could we do event-related stimulation? Like, for instance, I'm not an expert in this, but I read a publication about so-called conflicting Pavlovian situation. And there was observed that there's a specific burst in the frontal parts of the brain, and whenever that burst is missing, then the trial of the subject failed. You could ask questions like, when I measure fast enough that this burst is missing and I inject it with my stimulator, do I correct the trial? Things like this could be investigated. I wouldn't say answered, but at least investigated. And one last word about timing. The timing needed is strongly depends on the question. If you're dealing with the alpha rhythm and you're satisfied with like 5 degrees of being off, you need like 10 milliseconds. You have like 10 milliseconds. When you're dealing with gamma, you're going down to 1.5 milliseconds. When you look into phase resets in a fast rhythm, so a lot of rhythms do something like this. Oops, yeah, that was a phase reset. Alpha is reported, but also others. You need to be much more precise. And it also depends on your hardware. If you have like 2% missed events, but have like 30 components, you have like a 50% of failure of the measurement. And of course, it always depends, does your code need some shared resources like memory, stuff like that? If you do, you would have race conditions and you could observe logs, so testing would be much more complicated. And the last word, determinism means determinism, not probability and not speed. So real-time system is not by definition faster. In fact, the FPGA runs only at 40 megahertz, which is nothing compared to the 3 gigahertz any ordinary laptop runs. But when you tell the system to use exactly 50 nanoseconds, it does exactly this, and it does this also in 10 years. By the way, these machines are the computers which drive systems to outer space. And these are the control systems for satellites. This is a program which is not giving you a blue screen after some hours. This is supposed to run in 30 years again, still. You switch it on and it runs, and it keeps running. And this is quite, also the whole manufacturing is quite different. So these systems are guaranteed to work from minus 20 to plus 70 degrees. The simple ones, you can extend this and stuff. So this is quite a different hardware we're talking. So, and to end this talk, I would give you a small overview of what we're doing in the modeling part of our group. Most people do modeling actually in our group. So we want to do whole brain models. So we start with a more or less simple network of artificial neurons. In this case, this is an excellent, so adaptive, exponential, integrated fire neurons. So when we do this, we have an excitatory population, the red one, and we have an inhibitory population, and they are both fed by the outside with input, and they're interconnected. So this group is connected to that group and vice versa. When we do this, when we model like 40,000 neurons, we have like 80,000 equations to solve the time step. Well, that takes some time, and that is not nice. However, in 4 or 5 PhD works, we were able to reduce the model to 8 simple ordinary differential equations. These are fast to compute. And when we compare the systems, this is on the left side, we see a simulation which ran like 1.5 months to get the data of the different regimes. So what plotted here is the input to the excitatory connect versus the input to the inhibitory connection. The I is missing, sorry, it's here. And we see different regimes. We see all neurons are doing more or less nothing. It's the down state. All neurons fire. That's the up state. That's both the uninteresting part. What's interesting is these cycles here. What happens in bistable states? And so some neurons are doing this in this oscillation. Some neurons are doing a different thing. And these limit cycles, these are very interesting. And all our data show or suggest, I would say, the cooperation with Greifswald, where we deal with sleep and memory. Well, actually, it's about memory consolidation, not with sleep. But we see that all the interesting parts, all the interesting stuff happening in the brain are happening here. They are happening in these small cycles. And then there was another PhD who tried to model how an electric field, because this is what we do in electric simulation, interferes with this. Now, all of these neurons are point neurons. So for an electric field to work, you need some distance, you need some elongation. So he extended the model, which is a ball model, a pointwise model, and called the ball and stick, because it now has also a stick attached to it, which actually works as an antenna for the electric field. And he was able to build into these ordinary equations a simple term, which is an equivalent extra current just due to the electrical field working on the elongation on the dendrite. And then we, of course, it's a colleague of mine, Shala Chakan, did some simulation, and we found very interesting that although this is a very rough and rude model compared to a brain, is that when we look for frequency entrainment, we would need way too high current densities. 3 volt per meter is actually by nobody considered safe. Yeah? But we get a frequency drive in this system, but only if we drive it real hard. Now, phase entrainment, this is why it's green, we can observe in the area of 1 volt per meter, which is more or less the right regime. This is actually what happens if you do 2 milliampere and have good electrodes and stuff. Okay. And at the end of the day, we have a whole brain model which we can use to predict system changes, switches between states, and maybe in the next 5-10 years, we would have then better understanding what actually the term brain state would mean. And with this and some acknowledgements, because I didn't do all the things alone, I would close the talk. So the main investigator, I did everything was Dr. St. Schmidt, and these were the people from the medical department helping with some experiments, and it's of course only part of the data show. Thank you for your attention, and I'm happy to take any questions.